Hello everyone. During today's class, we are going to start with the first topic of the 4 that make up Module 3 of the study of the dynamics of the point of systems. In this module, we are going to approach 4 topics. A first topic, today's class, the introduction, to continue with the exposition as detailed as possible and as clear as possible of the 3 laws of Newton that we know and that we are going to analyze with all the details. We are going to analyze the physical magnitude of the quantity of movement. And at the end, what we will do will be to apply all the magnitudes and all the laws and principles studied through different simple examples to have clear the methodology and all the analysis that we have to take into account. We do not have to forget that during the 2 previous modules, what we have approached has been the kinematic study of the movement of the bodies. I mean, in that study, what we have done has been to analyze from a descriptive point of view simply how the bodies were moving. In this module, we are going to change the approach a little bit. We are going to continue analyzing the motion of the bodies, but now we are not going to worry only about describing that motion. We are going to worry more about analyzing why. What are the causes of the state of rest or motion of the bodies? We are going to focus on that. Beginning therefore with this first introductory topic, we will be concerned with seeing the origin of how we arrived at the general approach to the dynamic study of the macroscopic world we know, and then we will continue with an analysis of the forces that will govern the changes in the state of rest or motion of the bodies. To carry out all this study, we have the help of our 2 new friends. But since we know them from the 2 previous modules, Amanda and Jota, to carry out all the analysis, all the study, they will support us and they will share with us their 2 great passions, sports and the adventure of knowledge. We are going to focus, therefore, within this study of mechanics in this second block on dynamics. And we are going to focus, as we have mentioned, on the causes of the change in the state of rest or motion of bodies. How we finally arrived at the formulation of the laws governing the dynamic behavior of systems in the macroscopic world was from observation of everyday scenes, as we have here. Here we have Jota simply throwing a ball. We all know that when we throw a body upwards, the logical thing, what we expect, is that it reaches a maximum height and then spontaneously evolves to a minimum height that will be imposed by the conditions of the environment. Another everyday experience for us is, and that we know, is that when we throw a ball, the trajectory that it describes is not simply a rectilinear trajectory, but it is a parabolic trajectory, described by a parabolic line. All the kinematic quantities that describe this trajectory have already been analyzed in the first 2 modules. You have analyzed the position vectors, the velocity vectors, and the acceleration vectors. But why does it describe this parabolic trajectory, not a rectilinear trajectory? That is what we are going to analyze in the following topics. Also, the number of people and the number of scientists who were analyzing how motion occurred in the macroscopic world was from observing common effects, common situations in our environment. For example, the trajectory of celestial bodies, the trajectory of stars, of the moon, the change in the tides of the Earth's oceans, the trajectory of the sun. He wondered why these trajectories or these accelerations occurred in the way they were observed. And he was one of the greatest scientists we have ever had, Isaac Newton, who through observation and analysis of everyday experiences for him, together with all the knowledge they had from the contributions of previous scientists, came up with the formulation of what are known as the 3 laws of classical mechanics that govern the description of motion in the macroscopic world as we know it today. And how he arrived at the formulation of those 3 laws is captured in one of his famous phrases, in which he says that if I have been able to see farther, it has been because I have stood on the shoulders of giants. Newton was thinking of scientists before him, such as Aristotle, Copernicus, Kepler, Galileo, who through observation and analysis of the world around them, the macroscopic world, resorted to experimentation, to develop laws that tried to explain the phenomena they observed every day. If those laws or hypotheses were in agreement with the experimentation they were carrying out, those hypotheses acquired the rank of laws. Otherwise, what they had to do was to elaborate new hypotheses that would complement or rectify the initial hypotheses. In the end, when we had a global description based on those hypotheses and with the experimentation that was in agreement with them, those hypotheses acquired the rank of law or physical principle. What they were doing was applying the scientific method, applying the 4 key guidelines in the scientific method: observation, analysis, experimentation, and verification. All the detail of the formulation and analysis of the 3 laws that govern the macroscopic world is contained in Newton's famous book of the mathematical principles of natural philosophy. There we have them collected. One detail we do have to take into account that the scope of application of these 3 laws is in the macroscopic world, as long as we are analyzing phenomena where the velocities are not velocities close to the speed of light. That is, we are in a range of everyday speeds for us, such as the speed when we are walking, running, cycling, the speed of cars. But if we talk about phenomena where the velocities involved are of the order of the speed of light, we have to resort to what is known as relativistic physics. Classical mechanics, Newton's 3 laws that define this classical mechanics, are not valid in that context. Another area in which the application of Newton's 3 laws is not valid is when we want to study phenomena at the atomic or subatomic level. In that case, we should study the whole theory and all the laws encompassed in what is known as quantum mechanics. Taking into account the scope of study, therefore, and in the framework in which we are going to stay, the first thing we have to do to try to understand why a body is in a certain state of rest or is changing its state of motion is to see the causes, the interactions that the environment is performing on it. These interactions, we are going to represent them by a concept, a mathematical concept we can call the concept of force. And the first thing we have to ask ourselves is, let's see, this is our object of study, we focus our attention on it, and who is causing interactions on it? When it comes to asking who, or what is causing some kind of interaction on the body, let's make a first big division, 2 big groups. Let's think about actions that are acting on the body at a distance. And indirect actions, contact actions we could call. Among the actions at a distance, we have actions very familiar to us, as is the action of the terrestrial gravitational field, which is the origin of the force weight, very familiar to us. We have the force of gravity, therefore, and we also have the electromagnetic force. And among the direct actions, we have a lot of examples to deal with. For example, the actions of ropes directly applied on bodies, which give rise to tensions. Direct actions due to planes that are in contact, as for example, when it is intended to produce a relative displacement between 2 surfaces in contact and appear immediately by normal forces, the frictional force, and other types of force that we will be addressing and analyzing in the examples, such as elastic forces. Taking into account this basic scheme, we will focus on the methodology that we have to follow to approach the study of the change of the state of rest or motion of the bodies. In this image, we have Jota about to kick the ball. If we want to analyze how this ball is then going to come out, the motion from a certain state in which it is, we can say that here it was stationary, how it is going to come out when Jota kicks it. We are going to see the immediate forces that we have to take into account. On the one hand, we know that on Jota is going to be acting the force of the Earth's gravitational field, therefore its weight. Applied at the point representative of Jota, that point is defined as the center of mass of Jota. For the moment, we are not going to go there, but we will take into account that we will start or look at a point that represents the point of application of the force, the effect of the force weight. Another force that we have to consider is that to perform the kick, Jota is going to rest with his left foot on the ground. Then the reaction to those 2 contact surfaces, the foot and the ground, we have the normal. And in addition, we have when the impact occurs, the force that with the right foot is going to give Jota on the ball. We have therefore our object of study, the ball, and different types of forces involved. We are going to analyze different examples that are familiar because you have analyzed them in the previous modules, and we are going to isolate the body of study in these 2 examples that I am going to show you here. When you're throwing, when Jota wants to throw in one of his basketball drills the ball, we're going to focus our point of attention on the ball, and we are going to see the interactions to which that ball is subjected. In this case, in this first image, he is about to throw the ball what kind of interactions do we have to consider to which the ball is subjected? Well, we have the normal one, due to the action or the point of support of the ball on Jota's hand, and we have the weight force of the ball. In the image on the right, just at the moment of impact of the ball with the court, with the glass that supports the basketball basket, we have, at the point of impact, the reaction also, the normal, and we still have the weight force. What do we have to take into account? Therefore, we fix the attention to the body of study, and on it we apply all the interactions that are acting on it. In this example, let's fix the attention on this blue body, okay? On it, immediately we know that they're acting. If it's at rest on this horizontal plane, the ground is acting, the normal. Between the two surfaces in contact, on our blue body, this red representative vector up, the weight force down. And furthermore, let's assume that it is acting this force that forms a certain angle with the horizontal direction given by this angle alpha. When analyzing the forces, it will be easier if we consider the reference systems as you have studied them in the previous two modules. We will consider a horizontal axis, the x-axis, for example, which we are used to call the vertical axis as y-axis, and we will try to decompose all the forces that are acting on these two axes. We are going, therefore, to have that the normal force and the weight force are in the direction of the y-axis. Opposite directions, but both in that direction. But the force that is acting with this alpha angle with respect to the horizontal, we are going to decompose it into an x component and a y component. How? With the typical laws of trigonometry, f times the cosine of alpha will give us the x component of the force, and f sin of alpha will give us the y component. At the time of working with them, we are going to forget about that force. In fact, the one that was acting, but we are going to work already all with components. And so we will do all the study in horizontal components and vertical components. Another example, in this case, we have the example of the simple pendulum. We have a mass, a little ball that hangs with respect to a point. The ceiling can be by means of a cable. What forces we have to consider that are acting on this little ball that are going to govern its movement? And its motion, we know, is going to be a trajectory, like this one here, represented by the green dotted line, a circular trajectory with the center, the anchor point of the rope. And we know that it's going to move relative to, from experience, we know, relative to this equilibrium position. The forces that we have to consider are, and we know that they exist, the tension due to the anchor point with the rope and the weight force. We are going to do the same as before. We are going to decompose the forces according to a system of axes. In this case, we are going to take a system of axes solidary to the trajectory of this particle. My horizontal axis is going to be this one here, my vertical axis, this one here, the one that gives me the string. With this, I know that the movement, the velocity of the particle, which is tangent to the trajectory, will be given by this vector here, which would be who? This vector here, in this case. This axis here will have as a force that is contained in it the x component of the weight, p times the sine of the angle, in this case. While in addition, I have to consider that the rest of the contribution of the weight is contained in the y-axis, it would be for us p times the cosine of the angle of. We do the same as in the previous case. We will no longer consider this force that is not contained in the system of axes chosen, and we will work with the components of the weight, which would be the component on the x-axis and the component on the y-axis, when doing all the analysis. This is going to be the methodology we are going to choose from now on. We will always focus our attention on the point, on the body of the study, and we will introduce all the interactions to which the environment is subjecting it. Amanda helps us to summarize a little bit the ideas that we have to be clear about and that we have analyzed in this first introductory topic. We are always going to represent the interactions of the environment on the bodies by force vectors. Then it is very important to take into account all the vector information, module, direction, and sense. We have a lot of variation of forces. We have forces acting at a distance, directly applied forces, such as weights, stresses, normal forces that appear between planes in contacts, and when taking into account all the interactions, we have to take into account that since they are vector forces, we have to use vector algebra. So much for today's class. In the next class, we will give the whole expression and formulation of Newton's 3 laws. We will see each other then.